Now, in this lecture video, we're going to look at how to characterize the quality of estimators. And so the first topic we're going to look at, the first characteristic that we're going to look at of an estimator is the bias of an estimator. So let x1, x2, and so forth up to x sub n be a random sample from a population with an unknown parameter which we'll denote by theta. Now let's denote an estimator of theta by theta hat. And we will, if we want to emphasize the fact that this is a function of the sample, we might denote it this way, theta hat, and then as a function of the sample values. But typically, we're just going to, that will be understood, and we'll just denote this estimator by theta hat. So theta hat is an estimator of the unknown parameter theta, and it's computed from the sample. Now, since theta hat is a function of a random sample, it itself is a random variable, and it therefore has a sampling distribution. Now, denote the mean of its sampling distribution by either of these two notations, and we've seen this, we've talked about this concept before, and we've seen this kind of notation before. So we'll let mu sub theta hat denote the mean of the sampling distribution of theta hat. We could also denote that by this expression or this notation, the expected value of theta hat. These two pieces of notation represent the same thing, the mean of the sampling distribution of theta hat. Now the bias of theta hat as an estimator of theta will be denoted this way, and we read this as the bias of theta hat as an estimator of theta. And it's defined to be the difference between the mean of the sampling distribution of theta hat and the parameter theta. Okay, so that is the definition of the bias of theta hat as an estimator of theta. So with that, we can define what it means to be an unbiased estimator of theta. An estimator, theta hat, of a parameter theta is called an unbiased estimator of theta if the bias of theta hat as an estimator of theta is 0. In other words, if the mean of the sampling distribution of theta hat is equal to theta itself. So when that's the case, when the mean of the sampling distribution of an estimator is equal to the quantity that we're estimating, then we call that estimator an unbiased estimator of that parameter. Now clearly, the bias of theta hat as an estimator of theta is negative if and only if the mean of the sampling distribution of theta hat is strictly less than theta. In that case, we say that theta hat tends to underestimate theta. On the other hand, the bias of theta hat as an estimator of theta is positive if and only if the mean of the sampling distribution of theta hat is strictly greater than theta. And in that case, we say that theta hat tends to overestimate theta. Now, you'll remember back from our discussions about the sampling distribution of the sample mean that we said that when we're sampling from a particular population that has a mean of mu, then the mean of the sampling distribution of the sample mean is also equal to mu. And so in the language of what we're talking about here, that would imply then that the sample mean is always an unbiased estimator of the mean of the population from which we've obtained the sample. And so that is one of the reasons that we use the sample mean to estimate a population mean, because we know that that sample mean is unbiased as an estimator of that population mean. Now the next topic we're going to look at is the mean squared error of an estimator. Now let theta hat be an estimator of a parameter theta. The mean squared error, or MSE of theta as an estimator, the mean squared error of theta hat as an estimator of theta will be denoted this way, the MSE of theta hat as an estimator of theta. And it's defined in the following way. It's defined as the expected value of the square of the difference between theta hat and theta itself. Now it can be shown that the mean squared error, the MSE, is equal to the sum of the variance of the estimator and the square of its bias. In other words, the MSE of theta hat as an estimator of theta is equal to the variance of theta hat plus the square of the bias of theta hat as an estimator of theta. Now, what I would like you to do as an exercise is see if you can prove this relationship by using properties of expectation. Now, the MSE of an estimator is a measure of its quality that takes into account both its accuracy via the magnitude of its bias and its reliability via its variance. Now, I think it should make sense to you that the more variable an estimator is, the less reliable it is. The more variation, or the more spread out, the more dispersed the sampling distribution of an estimator is, the less likely it is to be close to the mean of its sampling distribution. And so in that sense, it becomes a less reliable estimator as the variability associated with that estimator increases. Conversely, if we think of the variability of an estimator getting smaller and smaller, then the smaller the variability is, the more reliable the estimator is, because the greater probability is that the estimator will take on a value close to the mean of its sampling distribution. So when we think about the quality of an estimator, there are really two things we want to take into consideration. We want to take into consideration the bias of the estimator, and that gets to its accuracy. We also want to think of the reliability through its variance. So the MSE, the mean squared error, takes into account both of those characteristics of an estimator. Now, since we would like for the magnitudes of both the bias and the variance of the estimator of an estimator to be small, the smaller the MSE, the better. Now, the MSE will always be a positive value. And so, when we have two or more estimators that we can choose from, we might want to think about the quality of those estimators and pick the estimator that is best in some certain sense. And one way to do that would be to choose an estimator that has the smallest variability, the smallest variance, the one that's most reliable. But if we only focus on the variance, we're ignoring the bias, and therefore we're ignoring the accuracy. On the other hand, if we only think about whether or not an estimator is biased or not, then we're really not taking into account the reliability of the estimator. And so what we want to do typically would be to think about or choose an estimator that has the smallest MSE possible. So the smaller the MSE, the better. Now note that if theta hat is an unbiased estimator of theta, then its MSE as an estimator of theta is just its variance. And this is because, remember that the MSE of theta hat as an estimator of theta is equal to the sum of the variance of theta hat plus the square of the bias of theta hat as an estimator of theta. But if that bias is 0, then the MSE just turns out to be equal to the variance of theta hat. Okay, now the next thing I want to talk about is the sampling distribution of the sample variance. And so let's let x1 through xn be a random sample of size n from a distribution that has mean mu and variance sigma squared. We'll let x bar be the mean of the sample and s squared be the sample variance, the version of the sample variance with n minus 1 in the denominator. So this is the sample variance that you're used to from your methods classes. And so we want to think about the sampling distribution of the sample variance. In other words, some questions to be considered. What is the mean of the sampling distribution of s squared? What is the variance of the sampling distribution of s squared? And can we somehow, or at least in some situations, find the PDF of the sampling distribution of S squared. And so you'll remember that we thought about these same kinds of questions in the context of the sampling distribution of the sample mean back in the module on sampling distributions. And so at this point, we're going to consider those same kind of questions for the sample variance. And so the first thing I want to point out, what we're going to do here is we're going to be determining the mean, deriving the mean of the sampling distribution of the sample variance. And the first thing I want to do is let's consider the numerator of the sample variance, the sum of the squared deviations of each observation around the mean. And note that we can rewrite this as the sum, k going from 1 to n, of x sub k minus mu squared, and then minus, we're going to subtract from that sum of squared values, we're going to subtract n times the square of the difference between x bar and mu. So that's a nice decomposition, or a nice way to rewrite the sum of the squared deviations around the mean. And so what we want to do is we want to now take the expected value of the numerator of the sample variance, and using this decomposition that we came up with on the previous slide, we can see that the expected value of the sum of squared deviations about the mean is equal to the difference between the expected value of the sum of squared deviations around the true value of mu minus the expected value of n times the square of the difference between x bar and mu. Now, because of the linearity property of the expectation operator, I can rewrite the expected value of the sum of these squared deviations, as the sum of the expected values. And I can pull the n outside of the expectation operator in this second expectation. Now, if we look at each one of these terms in the sum, we see here that we have x sub k minus mu quantity squared, all right, and we're taking the expected value of that. Well, you'll recognize that as being the variance of x sub k. And then over here, in this second expectation, remember that mu, that the mean of the sampling distribution of x bar is equal to the mean of the population that we're sampling from, in this case mu. And so we have the expected value of the square of a random variable, the difference between a random variable and its mean. And so that is just the variance of x bar itself. And so we have the sum k going from 1 to n of the variance of x sub k minus n times the variance of x bar. Now, because the x's constitute a random sample, they're independent and identically distributed, they all have the same variance. And so the variance of each x sub k is just sigma squared. In addition, the variance, you'll remember from our lectures on from Module 2, the sampling distribution module, that the variance of the sample mean is equal to the variance of the population we're sampling from divided by the sample size. And so that's sigma squared over n. And so we're adding up sigma squared n times, so that's just n times sigma squared. The n's over here cancel, and so we see that the expected value of the sum of squared deviations about the sample mean is equal to n minus 1 times sigma squared. Now remember that s squared is equal to 1 over n minus 1 times the sum of squared deviations about the mean. And so that we can use this now to find the expected value of s squared, or in other words, the mean of the sampling distribution of s squared. And it turns out, using the results that we've just obtained, along with the linearity property of the expectation operator, that the mean of the sampling distribution of s squared, the expected value of s squared, is just sigma squared itself. And so this implies that the version of the sample variance presented in introductory methods classes, again given here, is an unbiased estimator of sigma squared, the variance of the population from which the sample was obtained. Now let's look at an alternative estimator of the population variance. So let's consider another version of the sample variance where instead of dividing the sum of squared deviations around the mean by n minus 1, we divide it by n. All right, and so to differentiate it notationally from the usual sample variance, let's call this S star squared. Now, S star squared is perhaps the more intuitive way to calculate a sample variance, at least for students new to statistics, given that the variance is often described as the average squared deviation about the mean. And it also often comes as a surprise to students that statistics textbooks and statistics teachers highly recommend, in fact, we insist upon using the version of the sample variance that has n minus 1 in the denominator rather than this version. So I think that in many cases, students, when we start talking about a sample variance, they think that we ought to be dividing the sum of squared deviations by n, and they get surprised to see and to hear that we are going to divide it by n minus 1 instead. But now, we're now in a position to find out the reason for that recommendation. So note that we can write S star squared, the version of the sample variance that has n in the denominator, in terms of S squared, the version of the sample variance that has n minus 1 in the denominator. We can rewrite it this way. So S star squared is equal to n minus 1 over n times S squared. And so we can find the mean of the sampling distribution of S star squared by taking the expectation of S star squared. So that's the expectation of n minus 1 over n times S squared. By the linearity property of the expectation operator, we can pull the n minus 1 over n out. Okay? You'll recall from what we just did that the expected value of S squared is sigma squared. And so we see here that because n minus 1 over n is strictly less than 1, we see that the expected value of S star squared is strictly less than sigma squared. In other words, the mean of the sampling distribution of S star squared is something less than sigma squared. And so because the mean of the sampling distribution of S star squared is not equal to sigma squared, S star squared is not an unbiased estimator of sigma squared. It's biased, and in particular, the mean of its sampling distribution is strictly less than sigma squared, and so S star squared tends to be a little bit too small. It tends to underestimate the true population variance. Now, the bias of S star squared as an estimator of sigma squared, you'll remember that that's defined to be the difference between the mean of the sampling distribution of the estimator and the parameter that we're trying to estimate. And so the bias of S star squared as an estimator of sigma squared is equal to the expected value of S star squared minus sigma squared. So that's equal to n minus 1 over n times sigma squared minus sigma squared. And that turns out to be negative sigma squared over n. So the bias of S star squared as an estimator of sigma squared is negative, number one, right, because it tends to underestimate sigma squared. And it depends on both sigma squared and n. Now you can see that as n increases, this quantity is going to get closer to 0. And in particular, as n goes to infinity, the bias is going to converge to 0. And in addition, the mean of the sampling distribution of S star squared will converge to sigma squared. And so you see here that this problem of bias diminishes, becomes less of an issue as the sample size gets larger. Okay, so now what I want to do is I want to compare these two estimators of sigma squared, and I'm going to use a little bit different notation. I'm going to use sigma hat squared to denote the unbiased version of the sample variance. So this would be S squared in our previous notation. And I'm going to use sigma tilde squared to represent the biased version of the sample variance, so the version that we called S star squared. So this type of notation is in common usage, and I just wanted to use this so that you get used to this as well. So as we pointed out in a previous slide, we can represent what we're now calling sigma tilde squared as n minus 1 over n times sigma hat squared. And so we have shown in previous work up above that the expected value of sigma hat squared, the mean of the sampling distribution of sigma hat squared, is equal to sigma squared, and that the expected value of sigma tilde squared, in other words, the mean of the sampling distribution of sigma tilde squared, is n minus 1 over n times sigma squared, which is strictly less than sigma squared. And so from these two results, it follows that sigma tilde squared is an unbiased estimator of sigma squared, and sigma tilde squared is biased as an estimator of sigma squared, and it tends to underestimate sigma squared. And so before we go any further, I want to ask you just to consider this question: which of these two estimators would you consider to be a better estimator of sigma squared? Now, obviously, sigma hat squared is unbiased, right? In terms of what we might consider, what we might think of as accuracy, it seems to be pointing at the right thing, whereas sigma tilde squared is a little bit off, right? It's a little bit biased. In fact, in particular, it tends to underestimate sigma squared. But also remember that bias or unbiasedness is not the only characteristic that we consider when we're thinking about the quality of an estimator. We also want to think about the reliability of an estimator as well. So which of these two estimators might we think is more reliable? Well, what we need to do is derive the variance of the sampling distribution for each of these two random variables. Okay, so in order to do this, we're going to look at a special case. And we're going to look at this special case for two reasons. Number one, because coming up with the results is a bit easier for us, and it's appropriate for this level of theory class to focus on these things. Plus, this is the situation that we're going to find ourselves in developing methodology and so forth. So we're going to assume here that we're sampling from a normal distribution with mean mu and variance sigma squared. So the random variables x1 through xn are independent and identically distributed according to this normal distribution. Now, under that assumption, as we talked about when we were talking about the chi-square distribution, it can be shown that if we take sigma hat squared, multiply by n minus 1 and divide by sigma squared, we get a random variable that has a chi-square distribution with n minus 1 degrees of freedom. Now remember that the variance of the chi-square distribution is equal to 2 times the degrees of freedom. And so the variance of this random variable that has a chi-square distribution with n minus 1 degrees of freedom is just 2 times n minus 1. Now we can use properties of variance, and we can pull out the constant n minus 1 over sigma squared, but to do that we have to square that ratio. And so we have n minus 1 over sigma squared, quantity squared, times the variance of sigma hat squared being equal to 2 times n minus 1. Now we can then solve for the variance of sigma hat squared, and what we get is that the variance of sigma hat squared, and remember sigma hat squared is the version of the sample variance that has n minus 1 in the denominator. This is the unbiased version of the sample variance. The variance of this version of this estimator of sigma squared is equal to 2 times the square of the population variance divided by n minus 1. So that's a very handy thing to have. And we can now use that along with this relationship between sigma tilde squared and sigma hat squared. Remember that we can write sigma tilde squared as n minus 1 over n times sigma hat squared. And so now we can derive the variance of sigma tilde squared very easily. it's just equal to the variance of n minus 1 over n times sigma hat squared. We can pull n minus 1 over n outside of the variance operation, but to do that we have to square it again. We've got to be careful to do that. And so we have n minus 1 over n quantity squared times the variance of sigma hat squared, which we just found to be 2 times the square of the variance divided by n minus 1. And now we can do some simple algebraic simplification, and we find that the variance of sigma tilde squared is equal to n minus 1 over n squared times 2 times the square of the variance. Now, it's clear that the variance of sigma tilde squared is less than the variance of sigma hat squared. All we have to do is look up at this particular line right here. We see that n minus 1 over n, quantity squared, that's going to be less than 1. All right, and so that means that the variance of sigma tilde squared is certainly less than the variance of sigma hat squared. Now let's consider the mean squared error of each of these estimators. The mean squared error of sigma hat squared as an estimator of sigma squared, remember that this is equal to the variance of sigma hat squared plus the square of the bias of sigma hat squared. Now, because sigma hat squared is unbiased, right, its bias is 0, and so the mean squared error of sigma hat squared as an estimator of sigma hat squared is just the variance of sigma hat squared. So 2 times the square of the population variance divided by n minus 1. The MSE of sigma tilde squared, again, is going to be equal to the variance of sigma tilde squared plus the square of the bias of sigma tilde squared as an estimator of sigma squared. And so we have n minus 1 over n quantity squared times the variance of sigma hat squared plus the square of the bias of sigma tilde squared, which is negative sigma squared over n. And we can go through some basic algebra, and we come up with the expression that which is equal to sigma, the square of the population variance over n squared times 2n minus 2 plus 1. And we can do a little bit more simplification. And so we get this expression, 2 minus 1 over n times the square of the population variance over n, to be the MSE of sigma tilde squared. Okay, so we've shown that the MSE of sigma hat squared is equal to 2 over n minus 1 times the square of the population variance. We have shown that the MSE of sigma tilde squared is equal to 2 minus 1 over n all over n times the square of the population variance. And so it's clear that 2 minus 1 over n all over n times the square of the population variance is strictly less than 2 over n minus 1 times the square of the variance. And so what we've shown here is that the mean squared error of sigma tilde squared as an estimator of sigma squared is less than the mean squared error of sigma hat squared, again, as an estimator of sigma squared. And so in summary, we have shown the following. We've shown that the variance of sigma tilde squared is less than the variance of sigma hat squared, and we've shown that the MSE of sigma tilde squared is also strictly less than the MSE of sigma hat squared. And so we can draw the following conclusions. From the standpoint of variability alone, in other words, from the standpoint of the reliability of these two estimators, sigma tilde squared is a better estimator than sigma hat squared as an estimator of sigma squared. Let me say that again. From the standpoint of reliability alone, right? And what we mean by that is the variability. The reliability and the variability are inversely related. So the greater the variability, the lower, the greater the variability, the lower the reliability. The lower the variability, the greater the reliability of the estimator. So from the standpoint of variation or reliability alone, sigma tilde squared is better than sigma hat squared as an estimator of sigma squared. Now, let me remind you here that sigma tilde squared is the biased version of the sample variance. And so what this is saying is that from the standpoint of reliability alone, the biased version of the sample variance is a better estimator of the population variance than is the unbiased estimator of the population variance. In addition, well, and let me just say that you might say, well, okay, yeah, when we think about reliability, we're not taking into account the accuracy. We're not taking into account the bias of the estimator. Well, okay, that's a good point. Let's take into account both the reliability and the accuracy, both the variability of the estimator as well as the magnitude of its bias. And we do that by looking at the MSE. So from the standpoint of the MSE, which takes into account both the variability and the bias of the estimator, in other words, it takes into account both the reliability and its accuracy, the biased version of the sample variance is still better than the unbiased version as an estimator of sigma squared. So that's interesting, I think. Is that surprising to you? What I want you to think about is, if that's the case, if the biased version of the sample variance is a better estimator of the population variance than is the unbiased version of the sample variance, then why in elementary textbooks and in elementary classes, why do we insist on using the unbiased version of the sample variance? In other words, the version with n-1 in the denominator. So I want you to think about that and see if you can come up with a rationale. But this is a good example to look at from the standpoint of looking at how to compare estimators. Typically, in a given for a given situation, or in trying to estimate a given parameter, we typically have more than one alternative, more than one option when it comes to estimators for a given parameter. In this example, we have the version of the sample variance with n-1 in the denominator. We have the version that has n in the denominator. For other parameters, we typically have more than one parameter as well, or more than one estimator as well. For estimating a population mean, we've got more than one estimator in that case as well. And so when we have more than one estimator available, we have to decide which one we want to use. And so we have to have criteria that we can use to compare these different estimators. And one of the most important and one of the most commonly used criteria is the MSE. And so what we're seeing here is that from the standpoint of MSE, the biased version of the sample variance is a better estimator than the unbiased version.